Hello guys, welcome back to Easy Tech Nest. In continuation with the previous lecture, now we'll discuss about the memory. Memory is classified into two types, on-chip memory and off-chip memory. In on-chip memory, the processor or controller contains built-in memory and external memory need not be connected in on-chip memory, whereas in off-chip memory, some processors or controllers do not contain any memory inside the chip and we need to connect the external memory. Further, memory is classified into primary memory. Primary memory is classified into two types, RAM and ROM. And ROM, which is called the code memory, has been further classified into flash, PROM, masked ROM, EPROM, double EPROM, and NVRAM. We'll discuss about each component in detail. First one is ROM. ROM, it stores the program instructions and it retains the contents even after the power to it is turned off, which is known as non-volatile. ROM memory is non-volatile storage memory and it's classified depending on the fabrication, erasing and programming techniques. First one we'll be discussing is MROM, that is masked ROM. It is one-time programmable and makes use of hardwired technology to store the data, whereas it is factory programmed by masking and metallization process. Advantages of MROM is low cost for high volume production. Disadvantage is we are unable to modify the device firmware, that is the software. As MROM is permanent, it is not possible to alter or make any changes. Next, we'll be discussing about PROM. PROM is called as programmable read-only memory. It is not pre-programmed by the manufacturer. The end user is allowed to program, but only one time. OTP cannot be reprogrammed and not useful for the development. Here is the overview of the PROM. Here you can see the NMOS fuses on the NMOS transistors that can be blown in order to disconnect from the device. It is like a switch. The fuses are blown in order to disconnect the NMOS transistors. Leaving the fuses intact produces logic 0. Here you can see logic 1 and logic 0 as the NMOS transistors are being programmed. Next, we'll discuss about EPROM. EPROM refers to erasable programmable read-only memory. During the development phase, the code can be changed and using OTP each time is not that economical. OTP here refers to the PROM. As it is only one-time programmable, the cost increases. EPROM gives the flexibility to reprogram the same chip. So we are using UV rays to erase the EPROM, but the disadvantage is it needs to be taken the circuit out of the board and put in a UV eraser device, but the erasing cost and time is very more, so it is tedious and time consuming. Next one is double EPROM. Double EPROM refers to electrically erasable programmable read-only memory. The information contained in double EPROM can be altered by using electrical signals. They can be erased and reprogrammed in the circuit and can be erased in a few milliseconds and provides greater flexibility for the system design. Next is flash. It combines the reprogrammability of EPROM and high capacity of the standard ROM. It is organized into sectors or pages and stores information in the form of an array. Next is NVRAM. NVRAM refers to non-volatile random access memory. It is random access memory with battery backup and the lifespan of NVRAM is around 10 years. Next, we'll be discussing about RAM. RAM is random access memory or read-write memory. It is a type of data memory, whereas ROM is a type of program memory. RAM can perform both read and write operations. It is volatile in nature, which means when the power is turned on and then turned off, all the contents are destroyed. RAM is classified into two types such as SRAM and DRAM. SRAM refers to static RAM and DRAM refers to dynamic RAM. In the next slide, we'll discuss about SRAM. SRAM is static RAM and stores data in the form of voltages and is made up of flip-flops. Flip-flops are sequential circuits with clock cycle, and sequential circuits are those circuits in which the output is dependent both on the present as well as the past values. So SRAM is the fastest form. An SRAM cell is realized using 6 transistors, 4 which we are used to build the latch and 2 for the control access. Here we can see this is the structure of SRAM, and the limitation is its low capacity and high cost. Next we'll discuss about dynamic RAM. It stores data in the form of charges. Therefore, the diagram of DRAM consists of a capacitor which is used to store the charges. They are made up of MOS transistor gates. Advantages is its high density and low cost as compared to SRAM. Disadvantages, as information is stored as charges, it may leak off with time, and to prevent this, it is needed to refresh periodically. Coming to the difference between SRAM cell and a DRAM cell. SRAM cell is made up of 6 MOSFET, whereas a DRAM cell is made up of a MOSFET and a capacitor. SRAM cell has low capacity, DRAM cell has high capacity. SRAM cell is expensive and does not require any refreshing operation to be performed, whereas DRAM is less expensive, whereas requires refreshing periodically. SRAM is fast in its operation and the access time is around 10 nanoseconds. In DRAM, the operation is very slow and the access time is 60 nanoseconds. Next, we'll discuss about the parallel and serial interface. Parallel interface is a type of interface in which the data is transmitted in a parallel way, and in parallel interface the time consumed is very less as there are different address buses and lines to transmit the data from the transmitter to the receiver, whereas in serial interface the data is transmitted one by one and hence the time lag consumed is very high. Next, we'll discuss about memory shadowing. Memory shadowing is a technique adopted to solve the execution speed problem. Sometimes there is delay in the processor that we use. Therefore, the concept of memory shadowing comes into picture. In this, the RAM access is about 3 times faster than the ROM access. In personal computer systems or BIOS, stores the hardware configuration information. Manufacturers include a RAM behind the logical layer of the BIS, as it's both have the same address as a shadow to the BIOS. So during the boot up, BIOS is copied to the shadowed RAM and RAM is write protected. Next is memory selection for embedded system. Embedded system requires a program memory as well as the data memory. Program memory is required for holding control algorithms or embedded operating system, whereas data memory is required to hold variables and temporary data. So the memory requirement for embedded system is dependent on the type of the embedded system and application for which it is designed. Considering the example of a simple electronic toy, microcontroller with few bytes of internal RAM flash and no need for external memory as it is a simple electronic toy, whereas in smartphones we need external memory sometimes when the storage is full. Embedded design for RTOS. RTOS refers to real-time operating system, requires certain amount of RAM for its execution and also ROM to store the RTOS image. Next is two parameters to represent a memory. One is size of the memory chip and another is word size of memory. Size of the memory chip, consider the address range supported by the processor, and in word size of memory, number of memory bits that can be read or written together at a time is considered. Flash memory. Flash memory is used as a ROM in embedded applications, mobile electronic devices and other consumer applications, whereas EEPROM, uh, it is used to in a processor of device to support serial interface, and amount of data to write and read is very less. It saves address space of this whole system. Next is sensors and actuators. Sensor, it is a transducer device that converts energy from one form to another for any measurement or control purpose. Whereas actuator is also a form of transducer device which converts signals to corresponding physical action. It acts as an output device. Next, we'll discuss about the I/O subsystem. I/O refers to the input-output subsystem. It facilitates the interaction of the embedded system with the external world. Examples of the I/O ports. Most of the I/O subsystem has I/O ports. Example of I/O subsystem devices would be LED, 7-segment display, and optocoupler, relay, piezo buzzer, and push button switches. In the further slides, we'll discuss about each of the I/O subsystem. LED. LED refers to light emitting diode. It is an output device for visual indication in any embedded system. Here the anode of the LED is connected to a resistor, and the resistor is supplied with a VCC or the voltage, and the cathode is connected to the ground. This is how an LED is interfaced. LED can be used as an indicator for uh, determining the status of various signals in situations whenever the device is on, battery is low, or charging of battery conditions. LED is a PN junction diode and it contains an anode and a cathode. For proper functioning of LED, the anode is connected to positive terminal of the supply voltage and cathode is connected to negative terminal of supply voltage. A resistor is used in series to limit the current through the LED. Next, LED can be interfaced to the port pins in two ways. In first method, anode is connected to the port pin and the port pin drives the LED to a very high logic, that is logic 1. In the second method, the cathode of the LED is connected to the port pin and anode to the supply voltage through a current limiting resistor. In this, the LED is turned on when the port pin is at logic low, that is logic 0. Next, we'll discuss about 7-segment LED display. 7-segment LED display is also an output device, and the current flow through each LED segment will be limited to maximum value supported by the LED display unit. The typical value supported is 20 milliamperes. LED 7-segment LED display is used in low-cost embedded systems such as public telephone call monitoring and point of sales terminal. The 7-segment display is an output device for displaying the alphabets as well as the numeric characters. It contains 7 LED segments arranged in a special form like this. And the LED segments are named from A to G, and a decimal point LED segment is named as DP. The LED segments A to G and DP should be lit according to the display numbers and characters. There are two configurations available in 7-segment LED display. One is common anode and another one is common cathode configuration. In common anode configuration, the anodes of all the 8 segments are connected commonly, whereas in commonly to the VCC, whereas in the common cathode configuration, the cathodes of 8 LED segments are connected to the ground or connected commonly to a single point. So this is how the configuration of common anode LED display and common cathode LED display works. Next we will be discussing about optocoupler. This is the circuit of optocoupler. It consists of an IR LED and it also consists of a photoresistor. The main function of optocoupler is it is used for suppressing the interference in the data communication, circuit isolation, and also high voltage suppression and signal intensification. It is a solid state device which is used to isolate the two parts of a circuit. It combines an LED and a phototransistor in a single package. Next, the component is a relay. Relay is an electromechanical device and acts as a dynamic path selector for both signal and as well as power. Here you can see the diagram of a single pole, single throw, normally open. This is normally open now. This is the single pole, single throw relay. Another one is single pole, single throw, normally closed relay. Here both the terminals are connected and hence the relay is in closed condition. Here we have another relay configuration, that is single pole double throw relay. We can connect to both the select lines one at a time, and it works on the principle of electromagnetics. When the voltage is applied to the relay coil, current flows through the coil, which in turn generates the magnetic field. This magnetic field attracts the armature core and also moves the contact point. The movement of the contact point changes the power or signal flow path. Next is piezo buzzer. Piezo buzzer is a piezoelectric device for generating audio indications in embedded applications. It is of two types, self-driving and external driving. In self-driving, the circuit contains all the necessary components to generate sound in a predefined tone. It will generate the particular tone on applying a particular voltage, whereas in external driving, it supports the generation of different tones. The tone can be varied by applying variable pulse train to the piezoelectric buzzer. Next is the block diagram of a piezo buzzer. It is connected to the microcontroller and the microcontroller is given a power supply of 3 volts. It is connected to a resistor, then to a transistor, and then to the speaker or the buzzer. Next is the working of push button switches. Push button switches are of two types, pull up push button and pull down push button. So the first diagram represents the pull up push button. In pull up push button, it is connected to the VCC, and here the ground is not connected, that is, which is an open circuit. As it's an open circuit, no current will flow from ground to the output and only VCC will flow. Therefore, the output here is VCC. And another configuration of pull up push button is in its closed condition. When it is in closed condition, the output is 0 as the ground is connected here. Next configuration is pull down. In pull down configuration, there are further divided into two configurations, that is pull down push button in open condition and pull down push button in closed condition. In the open condition, the VCC is not connected and hence the output is ground. And in the pull down connection with closed condition, as it is closed, the VCC will be produced at the output. Next, there are two configurations, push to make and push to break. It is used to make a circuit as well as remove the connection from a circuit. Depending on the way in which it is interfaced to the controller, it will generate either a high pulse or a low pulse. Next, communication interface. There are two types of communication interface, onboard communication interface and external interface. The communication channel which interconnects various components within an embedded product is referred to as onboard communication interface, whereas the external communication interface, uh, it can be either wired or wireless media or serial or parallel interface. Next is communication interface and various onboard communication interface and external communication interface. This we'll discuss in the next lecture. Thank you.